In this video, we're going to talk about something called print recursion, which can be a pretty interesting application of recursive functions. So let's say we wanted to do the countdown function here with an input of 0. So what this says is we would print out 0, see if I can write 0, and then we would, because 0 is not equal to 1, we'd call the countdown function on n minus 1. So because our n was 0, this we'll call countdown of -1. And what countdown of -1 does is it prints out -1. And because -1 is not 1, it calls countdown on -2, which that prints -2, and hopefully you're seeing that this is going to do a lot of printing. So this is probably going to be another Stack Overflow exception, crash, all kinds of good stuff. Now let's look at countdown of 1. What countdown of 1 does is it prints out our input, and then if 1 is not equal to 1, it would call the function again. But because it is equal to 1, it does not do the recursion, so the function stops. If we did countdown of 2, what it does is prints out 2, and then because 2 does not equal 1, it calls countdown of 1, and we know what that does. So let me actually write that here. We do countdown of 1. And we know that countdown of 1 generates a 1, so our total output is a 2 followed by a 1. If we do countdown of 3, it prints out a 3 followed by a call of countdown of 2. We know that countdown of 2 is a 2 and a 1, so we get 3, 2, 1. Visually what this looks like, and I'll draw this down here, there's a little area at the bottom for evaluation trees, is that if we want to do countdown of 3, what it's going to do is print out 3 followed by a call to countdown of 2. What countdown of 2 does is it prints 2 followed by a countdown of 1. And what countdown of 1 does is prints 1. And this gave us the output 3, 2, 1. So let's compare this to how count up 3 works. So for count up, and we put in first the number 0, something really funny happens. Because 0 does not equal 1, it calls count up of -1. Because when -1 gets passed in, -1 does not equal 1, it calls count out of -2. And -2 doesn't equal 1, so it calls count up of -3. So this result's going to be different than the last one. It's still going to be a Stack Overflow exception, and it's going to crash. But there is no output for this one. And the reason why is the prints don't happen until the recursion's done, and the recursion is never done. In this one, it prints before the recursion, so the fact that the recursion never finishes doesn't prevent the printing from happening. So let's look at count up of 1. Once again, 1 does not equal 1, so we don't do the recursion, but we print out the 1. So what does count up of 2 do? Well, 2 doesn't equal 1, so it does count up of 1, followed by the printing of 2. Well, we know that count up of 1 gives us a 1, so this is 1, 2. Count up of 3, because 3 does not equal 1, first does count up of 2, followed by the print of 3. So that means we get a 1, 2. Oh, well, that was a mess. I'm going to do that. So count up of 2 gives us both the 1 and the 2, and then we have the 3 afterwards. And so I want to look at how this tree looks different for count up 3. Because what it does first is it does count up of 2, followed by the print of 3. This one, count up of 2, first does count up of 1, followed by the print of 2. And what count up of 1 does is print 1. And this gave us the output of 1, 2, 3. So the moral of the story is that the order of the recursion matters. If you switch around the recursion, it actually flips the result. It makes it go in the reverse order. So that's something important to notice. If you look at the count up functions and count down, the only difference besides the name is that one prints before it recurses, and the second one recurses before it prints. And so that changes what the output's going to be. If we look at countdown up, lots of fun things happen here. So once again, if we put in 0, what's going to happen is it's going to print out 0, and then it's going to call the recursive function, because 0 does not equal 1, which calls count up of -1, which prints out -1, blah, blah, blah. So this is still a Stack Overflow exception and crash. Now, the more interesting cases is if we put in 1. If we do count down up of 1, it's going to print 1. It's not true that 1's not equal to 1, so it does not do the recursion, and then it prints 1 again. So what does count down up of 2 do? Well, it prints 2. 2 does not equal 1, so it does count down up on the value 1, and then after that it prints the 2. Now remember, count down up 1 gave us the output of 1, 1, so we've got 2, 1, 1, 2. If we do count down up 3, that's going to do the print of 3, followed by count down up 2, count down up 2, followed by a printing of 3, which is, because we know count down up 2 is 2, 1, 1, 2, we're going to have 3, 2, 1, 1, 2, 3. So if we look at the tree diagram for that, count down up, what it does is it first prints the 3, then it does count down up 2, then it prints the 3. Then count down up 2 will first print the 2, then do count down up 1, then print the 2. And then count down up 1, it just prints the 1, and then prints the other one. So it gives you 3, 2, 1, 1, 2, 3. Now let's look at double count. So this one, so just to compare them right away, count down up does print, recurse, print. Double count does recurse, print, recurse. So let's see what that does. This one's going to have no output when the input is 0 again, and it's going to crash because the recursion happens before the printing, and they have infinite recursion here because we're going to miss the base case. If we do the input of 1, it doesn't do either the recursive calls because 1 not equal to 1 is not true, so it's only going to print out the number 1. Double count 2, 2 is not equal to 1, so it's going to call double count on the input 1 less than 2, so that's 1, followed by the printing of 2, followed by the double count call of 1. So that means the total output, because double count 1 was 1, is 1, 2, 1. And then double count 3 first would do double count 2, followed by a print of 3, followed by a double count of 2. Now remember that double count 2 was 1, 2, 1, so altogether we're going to have a 1, 2, 1, followed by a 3, followed by a 1, 2, 1. So showing you that on the diagram, double count of 3 is going to do a double count of 2, a print of 3, and a double count of 2. Double count of 2 does a double count of 1, a print of 2, and a double count of 1. I always run out of room here. And then double count of 2 over here does the exact same thing. Double count of 1, a print of 2, double count of 1. Whew, barely fit that in, kinda. And the output that we get for this is 1, 2, 1, 3, 1, 2, 1. So if you like drawing these diagrams, I want to show you a way to figure out the output. What you do is you just start at the top and go around, and every time you hit a print statement, you put it out. So like 3, 2, 1, 3, 2, 1. If I do this one going around the tree, it goes 1, 2, 3. Kind of makes like a leaf. This one does 3, 2, 1, 1, 2, 3. Oh, I didn't finish this, right? Double count of 1 prints 1, so I need a bunch of print 1s here. I knew I missed something. Oh boy. Print 1. Yikes. Okay. So this one will print 1, 2, 1, go all the way up here, 3, 1, 2, 1. So this is a mess over here. But hopefully you get the idea of a couple things. The order of recursion matters. And then if you do these evaluation trees, it can help you figure out what the output's going to be if you know how to read them the right way.